Hello. So I'm going to talk about Bloom filter. So in the last lecture, we covered the basics of Bloom filter, and today the focus would be to derive the false positive rate. So Bloom filter is an approximate uh, data structure in the sense that if you have inserted a bunch of items to Bloom filter, then it can say definitely that the item that you're looking for is not in the Bloom filter, so that way it is good. But if you ask if there is an element and it says yes, then it is really saying probably, maybe, right? So that's the approximate membership query. So whenever it gives false positive or yes as an answer, then a refinement step is required. Now, the false positive rate could be controlled. So you can make false positive rate like 10%, meaning 10% false positives um, will be there when you do a bunch of membership queries, or you can make it as small as 1% or 0.1%. So how do you do that? That's what we are focusing. It has to do with how many hash functions that you use, how big is your uh, hash bit array, and that has to do with how much memory do you allocate per element. So per element, how much storage you are allocating, right? So there are parameters that govern the false positive rate, and that's what we are interested to cover today. So false positive occurs, false negative do not occur. We also looked on the fact that Bloom filter saves a lot of space because of using bit arrays. And let's take a look at uh, the basic idea. So you have a bit array. So I'm showing you a bit array here. So initially, all the positions in this bit array are zeros. That means none of the element has been inserted. And I've added a index array as well, but index is assumed to be there. So this has 11 positions, right? The size of this bit array is 11. So if you insert an element, then what will happen is you will calculate the hash of the element, and using the hash, that will give you the location. So there are many hash functions. So let's say h1 is the first hash function. So you'll apply that to a key, and that will tell you where should it be stored. So let's say you get a 6. So then you go here, look, index 6, and make this a 1. And you do that for other hash functions like h2 and h3. So here I'm assuming that there are 3 hash functions, but this number of hash functions could be tuned. So it's also fine to have only hash functions, and it will have implications on false positive and how well the data structure performs. All right, so hash function 2 will give you a value, and you'll go, let's say it gives the same key, it gives a 1, so you will mark this as 1, and hash function 3, let's say, gives you a 10. So you'll go to this location 10 and mark this as 1. So that's how Bloom filter remembers that a particular key, let's say, an arbitrary element was inserted, right? So that's the basic idea. And you also looked at this tutorial. This is very useful. It has you can insert a bunch of items and see how the bit array changes, and you can see false positives happening there. So We looked at this before. Let's take a look at query one more time. So let's say X was inserted, and this blue color is showing which bits became a 1 because of X. And similarly for Y, 3 hash functions were applied, and you have a. And then similarly, Z was inserted, and it made these violet or purple bits on, or turned them into a 1. Now, when you search for, let's say, W, was W inserted in the data structure? Does the data structure Bloom filter? This is a Bloom filter. Does it contain W? So you do a hash evaluation for 3 hash functions. Will give you 3 values. So you go there and you see a 1 is here, so that's good. You go here, you see a 1 here, that's good. But here you see a 0, so that means that W was not inserted, right? So the Bloom filter will say that W is not present, is not a member of Bloom filter, right? So that's a query operation. All right, so that was the query operation. If all 3 were 1, then definitely, I mean, not definitely, but maybe W was there. But since we saw it 1, 0, that makes us confident that the element was definitely, W was definitely not there. So you can read about the query from my slides as well. All right, so there are certain properties of Bloom filter. So there are different versions of Bloom filter, but generally we do not allow elements to be removed, because removing elements is tricky, because 1 bit position is actually could be being pointed to by different elements, right? So it's very tricky. If you remove it, then the correctness of Bloom filter will go away. And so you cannot remove elements. Also, the more elements that are added to the set, added to the Bloom filter, the larger the probability of false positive will be. So this is like, there is a finite amount of space. If you keep adding elements to the Bloom filter, then lots and lots of bits, a high percentage of the bits are going to be 1. And if the majority of the bits are 1, then false positive would also increase, because what are the chances that an arbitrary element hashes to 3 locations and you find them to be 1? So the chances actually increases as you enter more elements. So that's why one of the parameters that we look for in controlling the performance of Bloom filter is called B. And B is defined as how many elements, what's the size of the Bloom filter? Like in the previous slide, we saw that there were 11 bit positions, so n equals to 11. And then divided by what is the size of the input that was inserted, right? So let's say we inserted 10 elements, so the size of this set is 10. So B is how much space are we allocating per element. That's the definition of B, right? So we want this value to be large. We want more bits allocated per item. Okay, so we'll see this parameter as we do our analysis. So per element storage. And we'll see, the control or the relationship between how many bits per element, which is B equals to 10 here. That's what it is assumed. We'll have the 1% false positive probability. So 1% is actually a good number, because out of 100, 1 is a false positive. So data structure is good, right? Only 1% false positive. So minimum, if you have minimum false positive rate, that's actually a good thing for the data structure. So we will see that the false positive depends on number of bits, number of hash functions. So this bits is the bit array, and how many elements are inserted. So that is actually this parameter, and this parameter is captured by B. Right? And error probability is based on fraction of ones in the bit array. Yeah, how many are 1? Because that's the test for whether an element is there or not. So the error probability is based on how many ones are there. Now this data structure also has very interesting properties. because if you do operation on the data structure, for example, you're inserting items, you're querying items, the time complexity remains the same because you just invoke 3 hash functions or k number of hash functions, and then you look at those positions, see if they are ones or not, and either set those bit positions as 1 or check. So only k operations. The standard hash table, because of collisions, the number of times you have to keep looking for an empty slot in the array keeps increasing, right? Not keeps increasing, but it's very variable. For some elements, you do have to do multiple lookups to see an empty slot, or in a linked list based implementation, you do have to search through that linked list, like whether the element is there or not. So that's a variable cost, but here it's not variable cost. So Bloom filter has this interesting property. And since multiple hash functions can be evaluated independently or in parallel, so you can write a parallel algorithm as well for Bloom filter, because the hash evaluations for the keys, they are independent, they are not related, so they can be done in parallel by, let's say, multiple threads. So it's a good data structure. We also saw some applications, like there are tools in databases, like Postgres is related to database. Cassandra is a big data system. HBase is a distributed database. So many software use Bloom filter. We also saw some examples of malicious website, and this example we did not see. So Medium is a website, and it maintains a Bloom filter for each user so that it does not redundantly recommend a website to user. So Bloom filter holds some information so that you don't show the same content, same website, you don't recommend it to the user. So Bloom filter is used widely. Now the natural question that comes to mind is, I have a bunch of items that I would like to insert. How big should I make the Bloom filter? How many hash functions should I use? And what kind of false positive rate should I expect? Because if my software is customer facing, I need to know, what are the false positive rate? So this is a number that I'm interested to know. Now, the good news is that there is some theoretical model based on probability theory, and you can configure them. So you have a handle on these parameters. All right, so now we basically, after some introduction, some revision, now we are at the new content, that is false positive rate, how to derive a false positive rate. So can we say, like, if my hash table has 1000 bits, so that's how big the bit array is, I'm using 5 hash functions, and I'm going to store only 300 elements, right? So n equals to 300. Can I say what is the false positive rate going to be? So that's what we are looking at. And the material is provided to you. So this is coming from a book written by Tim Roughgarden, and his algorithms book has Bloom filter. So that's where this analysis is coming from. We will see that there is a trade-off. Like, there is not a good answer, but you can trade space with accuracy. So what does this mean? Is that if you use more space, your accuracy can improve. If you use less space, you're definitely saving on memory, but sacrificing on accuracy. So there is like trade-off. You gain in one thing, you lose in other thing. All right, so because this whole analysis is based on probability, in discrete mathematics, discrete math class, you would have seen probability concepts. So we'll just start from basic probability, And with some assumptions, we can do analysis on the performance of Bloom filter. All right, so let's say you throw a dice, unbiased dice. What is the probability of getting a 4? So the dice has 1, 2, 3, 4, 5, 6, right? So it has 6 faces. You throw it, what is the probability you'll get a 4? Okay. So there are 6 options there, 1 to 6, and 4 is only one of them. So 1 by 6 is the probability. What is the probability of getting an odd number in a throw of dice? So in a dice, 1, 3, and 5 are odd. The rest are even. So 3 numbers are odd out of 6. So the probability is half. Okay, so that's how we calculate probability. Now, there is a rule of combining 2 probabilities. So this is like and or sum or product. So we'll look at that. What is the probability of getting a 4 and then an odd number in 2 successive throws of dice? So you throw a dice once, you throw a dice the next time. So probability of getting a 4 is 1 by 6. We looked at that earlier. Probability of getting an odd number is half. So one after the others is like an and so there the individual probabilities get multiplied. So you get 1 by 12. Now multiplying 2 probabilities is very important in Bloom filter analysis as well, because you know, why is that? So we'll see that, you know, throwing a dice, there are a couple of options. So whenever an element is inserted into the Bloom filter, it can go into any position, right? So there are n positions in the bit array, and when you're inserting an element, if you use 3 hash functions, there will be 3 positions that will become a 1. So there is probability of, you know, in Bloom filter as well, similar to that. And since there are multiple events, like you keep on inserting elements, so that is like multiple events. So one happening after the other. So you do have to multiply probabilities, individual probabilities, to get you know, composition of those numbers. So that's why multiplying probabilities is important. Okay, so the rule is probability that 2 independent events both occur equals the product of their individual probabilities. So multiple events are there and they are independent, and so you can multiply them. Okay, so a few more. If a probability of an event A is 1 by 6, and we assume that the total probability is 1. So there are many events, but when you combine, it's 1. So if the probability of event A is 1 by 6, total probability is 1, then what is the probability of event A not happening? So it is 1 minus 1 by 6. So 1 minus 1 by 6, 5 by 6. So happens, 1 by 6 does not happen, 1 minus 1 by 6. Okay, good. Now, before we go to Bloom filter, there are certain assumptions similar to hash table. You know, there are some assumptions in hash table also. So the first assumption is uniform distribution of keys in the bit array. So as you insert elements, there's no clustering. We assume that you know, uniformly the bit positions will become 1. So this assumption is important. Otherwise, analysis is very difficult and will not get nice formulas. So analysis, because of assumption of uniform distribution of keys, the analysis will not be exact. Okay. Even then, it's like a model. You know, the model could be useful even if it is slightly wrong. So approximate and practically useful. So people find this model useful. So it's a model for false positives. All right, so let's go to Bloom filter now. Suppose a data set S composed of many numbers, let's say many elements, is inserted into a Bloom filter that uses m hash functions. So m was 3 in our case, in so many examples that we had. And the size of the bit array is n. Like 11 was the size of the bit array in our previous slides. What is the probability that the array's first bit is set to 1? Okay, so what is it saying? That you have a bit array, and the size of bit array is n. So there are like n slots. So 0 to n minus 1. So this is the 0, this is n minus 1. So these many slots are there in the bit array. And you're using m hash functions. You are interested in what is the probability that the array's first bit is set to 1. So the idea is, any given bit. So we can do analysis for the first bit, but then it will also be true for an arbitrary bit. So let's see, so because you're throwing, you're doing a hash function. The hash function could go to any of the bit position. It does not have to go to 0. It may go to 0. So there is probability involved. There's some probability of this bit becoming 1, but there is also some probability of other bits becoming 1, right? So can we calculate this probability? All right, so this problem is similar to throwing a dart. So look at this dart. There are 1 to 20 sectors, and you can throw a dart, and the dart can fall into any arbitrary region. So you can assume also that your bit array with 20 positions is like a dart, and whenever one hash function is used to insert a key, then it will hit one of the positions in the bit array. So it helps to think about the bit array as throwing a dart here, and your dart landing in one of the areas. Okay. So we can see that if there are 20 places where your dart can land, there is 1 over 20 is what the probability will be that your dart will land in any one location. All right, so let's keep going. Dot analogy, setting a bit to 1 on insertion. So assume there are n places a dot can land. What is the probability that a dot hits the first region? So 1 over, and it could have gone to any one of them. The probability that will go to the first one is 1 over n. So then we also saw one example where the total probability was 1, and then we subtract the event's probability, and that gave us what's the probability of the event not happening. So that's what is happening here. What is the probability that the dart will miss the first region? So that's the A0. So 1 minus 1 by n, probability of that event not happening. What is the probability that every dart will miss the first region? So then we have to think about, when we insert elements, how many darts get generated, right? So this is like an analogy. So if you insert one element, then you are actually using m insertions, because m hash functions will give you m locations, right? So for one element, you have m darts. And how many elements do you have? S. So that's why m times s number of darts would be thrown. Okay. So in total, s elements need to be inserted, and each element will require m hash functions to be evaluated, which gives you a position in the dart. All right. And we multiply the individual probabilities of all those darts together, as we saw in the product rule. We multiply individual probabilities of the events. So product of individual probabilities, m is the number of hash functions, s is the size of the set inserted to Bloom filter. Okay, so this is the probability that every dot will miss the first region. Now, what is the probability that some dot hits the first region? So again, we are, using the same 1 minus the probability of event. So we know that we calculated this probability before. So this was that, the first region will not be hit. But still, there is some probability that, some dot will hit the first region, right? So the probability that the first bit of the Bloom filter is set to 1 is 1 minus the probability of that event not happening, right? We had seen what is the probability that every dot will miss the first region. 1 minus that is that what is the probability that the first bit of the Bloom filter is set to 1, okay? All right, now this formula could be simplified. It can also be verified, right? Like if you do a thought experiment by changing, M, S, N, and whether the probability decreases or increases, we can verify that this is the probability of the first region being hit, being set to 1, because you are inserting so many items to the Bloom filter. It's probable that some of the dots will hit the first region. Now we can simplify this expression just to make the calculation easier, because 1 minus 1 over n, let's assume 1 over n to be 1000, so it is like 1 minus 0.001, and then you have to multiply that number so many times, so it's difficult to calculate. If you can simplify it, our model would be easier to calculate. There would be some approximation inserted, but it will make back of the envelope calculation easier. So let's look at how can we make this expression easier. And also remember that the false positive thing is not completely solved, because we are just saying one of the bit being set to 1. But for false positive to happen, if you're searching for something, then m of those positions need to be 1. So it's not only about 1 bit position having 1, but m bit position having 1. So that is false positive. Like all of them are 1. M hash, those positions are 1. Then you have a false positive. So we're not there yet, but we will simplify this expression. The basic idea is this is the individual probability for 1 bit. If you multiply this m times, you will get a false positive rate. So power m, okay? Power m, that's what you need to do. Then it becomes a false positive. All right, to simplify this expression, let us look at a graph of e to the power x and 1 plus x. So in this graph, you can see there are some values in x-axis and there are some values on y-axis, and e to the power x is plotted here and 1 plus x is plotted here, right? So this must be x, and these are the value for these functions. So what is being observed here at when you are at 0 or near 0, so x is in this narrow range where x plus delta, x minus delta are within the range close to 0, then e to the power x is able to approximate 1 plus x. So this is what we can see here. So now this expression is also in the form of 1 plus x. It's hard to see, but it is. So you can say 1 plus and minus 1 over n. So this is like a x here, right? So it is in this form 1 plus x, where x is minus 1 over n. So that is our x. So with this form, we can use e to the power x. So if x is equal to minus 1 over n, then e to the power x will be e to the power minus 1 over n, right? So this whole thing can be simplified as e to the power minus 1 over n. Okay, so e to the power minus 1 over n, and m over ms is the power exponent there. Now, in the earlier slide, I told you that per key storage, like how many bit of storage are we allocating per key, per element, is how many bit positions are there, how big is the bit array, and how many elements are we storing, size of the set. So this n over s, this one is reciprocal of, so we have s over n. So you can think of s here. So s over n is the reciprocal, so that's why it is 1 over b. Okay. So, and then m is 1 over b multiplied by m is m over b, right? This is a simplified formula. All right. Now we come to estimating the false positive probability. So a false positive occurs for a key that is not in S and has not been inserted to the Bloom filter if all the m bits are 1 after inserting the key in S. So that's the false positive. So what is the probability that a given bit is 1 minus e to the power minus m over b. So this is what we saw here. Now, probability that all m of these bits are set to 1 is multiply the same thing m times. So that is like power m, exponent m. And this could also be verified by checking what is the false positive rate when m and b are equal to 1, right? So m and b are equal to 1. It is e to the power minus 1, 1 minus 1 over e. That will give you a number. So that would be the false positive rate. So we expect high false positive rate if you use only one bit per key, right? So there's not enough space for all the elements because per key is, this number is very small. So you expect high false positive rate as well. But if per key storage is very high, then you assume the false positive rate to be less. So if b is infinity, this will make it 0, e to the power minus 0, e to the power 0 is 1. So 1 minus 1 is 0 to the power m. Yep. So we expect very small, as b tends to 0, false positive rate tends to 0. Okay, a very small number. So sanity check, makes sense. This formula gives you high false positive rate here, low false positive rate here, and that makes sense. All right, now trade-off between space and accuracy. So we derived the false positive rate here, 1 minus e to the power minus m over b to the power m. That's a false positive rate. So we see that this formula, it will depend on m and it will depend on b, per key space. Now, what is the best choice for m and b? So when we are deploying Bloom filter, we need to choose m and b. Like let's say we choose 10 hash functions. So, what should be the value of b such that, this whole expression is minimized, because this is the false positive rate and you want the false positive rate to go down. So what are the ideal values of m and b? Should we take b as 10 or 20, right? What are the values that we should try in order to make this go down? So, I mean, how do we do that? Well, we can plot this false positive rate formula. So let's say this is a false positive rate FR, and it will give you a value from 0 to 1, 0 to 1, assuming 0, is very less false positive rate, 1 means very high. It's like 0 to 100% is normalized at 0 to 1. So we can actually plot this. If we can plot this function, then we can see, how these variables are related. So because here we have three things to show. You have a m and you have a b, right? So you have a m here, you have a b, and based on what values of m and b you choose, it may give you a curve like this. So false positive rate decreases and then increases, right? So you may get some graph like this if you plot this on a graph. So using calculus, we can um, reason about what are ideal values for m and b, so that you get to the minima, right? So calculus, in particular differentiation, differentiating this function and then setting that to 0 and solving it, taking the second derivative also. So using calculus, we can solve this and get our answer for what is the best choice for m and b. Okay. All right. So we have some results. So using calculus, I mean, the book provides us a value. So from the book, ideal choice of m and b depends on this relationship, and that came after doing differentiation and equating that to 0 and finding the minima. So m equals to natural log 2 times b. So this is the relationship between m, which is number of hash functions, is natural log of 2 times b. So m should be greater than, it depends on what is the value of natural log of 2 times b, right? So this is how they are related. So here is an example. Let's assume b is n over s. So this is by definition. So number of bit positions in the array, the size of the bit array is 1000, and s is the number of elements that are inserted. So you inserted 8. You insert 125 elements. So per key storage for each element, it is roughly 8, right? So this evaluates to 8. So if b equals to 8, what should be the number of hash functions? So you just multiply by natural log of 2, and then you get approximately 5. So 5 hash functions is a good number if you're using per key storage as 8. Okay, so b is a number that you have because you have allocated a certain size of the array, and you have also inserted a certain number of elements in the Bloom filter. So you know this. So then you can have a rough estimate of what should be the number of hash function. And natural log of 2 is less than 1, so it is smaller than m. Smaller than b, sorry. All right, so if you have questions, I can definitely answer them once I'm back to class. So yeah, if you have question, please hold on to your questions and we can discuss them once I'm there. Right now it's just a recorded lecture. I cannot answer or even take your question now. So we we have derived this formula for false positive rate, and it relates to space requirement with false positive, because b has to do with space requirement, per key storage space. Now still you have e to the power minus m over b, and we know the relationship between m and b because m equals to natural log 2 times b, right? M equals to natural log 2 times b. So we can use that formula to simplify. And that's, in the case where we want the optimal choice of m, then we can simplify this formula. B cancels, so natural log of 2 remains. M is natural log of 2 times b, and this is minus, so this is 1 over e to the power minus 1 over e. Then this is now here e and natural log cancels. Okay, so using this rule, you can simplify this, because e is also related to natural log. So you have 1 divided by 2, right? And this is power ln 2b, and 1 minus half is half. So this is a simple formula. So under ideal situation, false positive rate is half to the power natural log of 2 times b. So this makes, it makes the model simpler, because you do 0.5 to the power a number, for example, 5. All right, so plugging in values for b equals to 8, it evaluates to 0.5 to the power 5.54, and that is 0.023. And in percentage, you multiply by 100, so you get about 2%, because it's 2.3, so about 2% false positive rate, and that's the error rate. More space b, less false positives. So this is given by how b will multiplying half many times will make this whole thing smaller. So more space b, less false positives. Okay, so now we have a question. So let's look at this question. This is related to the formula that we just saw, and the formula is false positive rate is 0.5 to the power natural log 2. So we solved it for b equals to 8. What would be the solution for b equals to 16? All right, so we interpreted our heuristic analysis of Bloom filters by specializing it to the case of 8 bits of space per key inserted into the filter. Suppose we were willing to use twice as much space, 16 bits per instruction. So the model says that we should have a smaller false positive rate, because we actually made per key storage higher. What can you say about the corresponding false positive rate according to our heuristic analysis? So this is called heuristic analysis because uniform distribution of keys, I mean, that is an assumption. So that's why it's not exact analysis, it's heuristic analysis, assuming that the number m of hash tables is set optimally. So here, the calculus was used to get a relationship between m and b so that the function is minimized. Choose the strongest true statement. So for this case, is the false positive rate less than 1%, less than 0.1%, less than 0.01, less than 0.001. So that basically, you can just do half to the power natural log of 16. So half to the power natural log of 2 times b, and b is 16. So it will be a smaller number than 2%. All of them are actually smaller than 2%. So without doing math, it's actually hard to know. All right, so half to the power ln to 16. If you use your calculator, you'll get a number like a very small number. If you multiply it by 100, you get in percentage, so 0.04%. And 0.04% is less than 0.1%. So this one is correct, 0.01%, but our answer came out to be 0.04, right? And 0.04% is higher than, so this will not be the case. All right, so the answer is B. All right, yeah, thank you very much. Yeah, unfortunately, I could not be in the class today. I am in Seattle. There is a conference going on here, and I'm presenting a research paper today in the conference. So see you on Tuesday. Thank you.